Hello? All right. All right, let's get going. Good afternoon, everyone. How are you guys doing? How was the conference? Yeah? I learned a lot? All right. So I know I have a kind of tough job. This is the last session, so hopefully you guys will find it interesting. I'm very excited about the technology. Hopefully you'll find it the same way. Before we get going, a little bit about myself. So my name is Igor Stanko, and I'm a program manager for data warehouse, in particular for parallel data warehousing. So how many people have heard about the PDW? All right, so today basically we'll be talking about the Columnstore technology. And I'll kind of switch back and forth a little bit between the Columnstore technology and how that works inside the SQL Server itself, and just a little bit about the PDW tool, because that's very next to my heart. All right. Let's see. Let's make this as interactive as possible. Feel free to ask me any questions as we go through. If you go too deep and if I feel that we won't be able to cover all the material, I'll probably stop you, and I'll stay afterwards and we can chat and continue the discussion. A little bit about my background. So I've spent probably 15, 16 years in data warehousing space. Initially, basically, I was focusing on implementing data warehouse solutions. And after that, I moved to actually developing the product that resolves the data warehousing space, if you will, or data warehousing problems. So lots of data warehousing experience on my side. All right, so here is the high-level agenda, what we'll cover today. So first of all, we'll talk a little bit about the trends. So hopefully nothing new to you guys. We'll reiterate basically what you guys already know, just quickly. Then we'll talk about the Columnstore principles, if you will. How many people played with Columnstore technology in 2012, SQL Server 2012? All right, so there's going to be a good refresher here at least. We'll spend a little bit more time explaining how this actually works. Then we'll talk a little bit about the new functionality that we are introducing in our upcoming SQL 14 release. We just announced CTP1 last week, so it's pretty fresh off the press. So we'll talk a little bit about what's new, what's changed. As we go through that, I'll try to contrast how things used to work and how it actually works right now. So at least for people who are familiar with functionality, will get to appreciate it a little bit more. Then we have the demo. The demo is going to be on PDW, but I'll say it's on PDW just for the purpose so we actually show PDW to some of you guys. But the same functionality works exactly the same in the box itself. And at the end, basically, we'll have some Q&A, so hopefully we get some time there. All right, so trends. So as I mentioned, basically, I've been in data warehousing space for the last 15 years, and every year I hear, oh, data warehouse is going to grow, data warehouses are going to grow, and they've been growing. So the first data warehouse that I built, it was 1 terabyte data warehouse. At that time, it was very large data warehouse. These days, it's, I would say, on a smaller scale, right? So the data is growing almost exponentially every year. That exposes basically some of the challenges from the technology perspective, right? So once you store the data inside the data warehouse, you want to offer that interactive reporting to people, right? So it's not just about storing vast amounts of data inside the data warehouse. It's also about how do you get the data now quickly and enable that data for quick analysis to the end user, right? Another trend is, price per terabyte, specifically on in data warehouse, is actually have been going down and down, and there is more and more pressure. How do we actually reduce the price and allow people to store more data within the data warehousing solution, right? And you see a quote basically from an analyst. I'm not sure how many people had the chance to actually interact with this person, but he's a data warehousing guy, has been following that space for a while, where he says actually that these days data warehousing solutions can almost completely switch to appliance-based solutions. And there is a couple of reasons for that, but I think one of the main reasons is that the appliances offer like MPP type of processing. So as you scale the data, how do you actually leverage the hardware and scale out functionality so you can actually deliver some of these interactive reporting too. But I think another concept that has been, and we'll spend time talking about it, is the Columnstore technology. So Columnstore technology has been purposely built and evolved to address the data warehousing use cases. And we'll talk a little bit about that. All right. So let's talk a little bit about the column store and how does that actually work. So traditional databases, RDBMSs, by default, you get the row store orientation. And there is a reason for that, right? They evolved around the OLTP use cases, and the idea was how do we actually enable a transactional support for very quickly within the database, right? However, that technology is not well suited for getting the data out efficiently, right? The main problem is basically what's the biggest bottleneck in the whole stack, if you will, in the RDBMS? Anyone? I/O, right? That's the slowest component in the whole stack, if you will. So the problem is basically that the row store technology scans the whole row and then filters the data depending on what the query is asking for, right? Obviously, there are lots of inefficiency there. That's where Columnstore technology came to picture. Right? The idea is that rather than storing data in rows, you kind of turn things upside down and start loading data or storing data in columns. So columns are physically separated and stored in a disk independent from each other, right? And the idea there is that, one, since you are since you're storing data in columns, now you're storing the data within the same data domain, right? So you have a better opportunity to compress the data better. So how many people know about the page compression in SQL Server, right? So what this allows to actually, rather than compressing within the page where you have different data domains, you can actually go just within the same data type and actually offer better compression compared to page compressed data. Secondary benefit is that at runtime, when you issue a query, you can actually go only after columns that you actually need in order to resolve and deliver the results for a given query, okay? Which ultimately leads to a reduced I/O and more performance at runtime. All right, so a refresher for those people who know Columnstore. For those people who don't know, basically it's just a basic introduction to Columnstore concepts. There are two main concepts, I would say. One is a notion of a row group and notion of a segment. A row group, you can think of it as a collection of a certain number of rows within the database. So let's assume it's 1 million rows within the database. And then the segment is basically data for one column within that row group. And the idea is that the data on the disk is stored as segments. So you take from this row group, you take one segment, one column, you store that as a blob inside on the disk, okay? As well as when you need to query it, the unit of transfer between the memory and the disk is actually segment, okay? All right, so let's go walk through kind of example, how does this actually work at runtime. So here is an example. I have a simple table with a couple of columns and rows. So traditional kind of table that you would see from a relational database. So the first thing that we do when the data goes into the column store is we create those row groups, right? We horizontally split the data into 1 million chunks. Let's assume for now it's 1 million prefix the size. So that's the first step. The next step, as you mentioned, then we take the the columns within that row group, and we split them physically, right? After that, we go and compress the data. We spoke about the compression within the same domain. So now within segment, we start compressing the data sets, okay? And once it's compressed, we store it that way onto the disk, okay? Now the question is, what happens when you have a query? So let's assume that we have a simple query that projects 1, 2, 3 columns, right? So you have a product key, you have a sales amount, and then you have a predicate on the order date, which is typical data warehousing use case, I would say, right? So what happens at runtime, the first thing that we do is that we know that what are the columns that are required in order to deliver the query results. So we completely eliminate querying the columns that are not needed. So first of all, you automatically eliminate lots of I/O, right? But we don't stop there. Since there is a predicate there, and again, this is just a simple example. Since there is a predicate there, we say, out of all the segments that I have for all these columns, there is actually no need to query every single segment, right? I can actually not even query the segments that are not necessary, automatically yet another time to reduce even further I/O. Okay? All right. The second innovation that has happened, so one is basically column store technology and how you store and split the data and how do you store that within the disk and what's the runtime behavior. The second technology piece that is important from the column store perspective is what we call batch processing. So the idea here is that traditional, or I would say relational databases, I would say SQL Server is one of those. Traditionally, the way this works is basically when you send a query to SQL Server, there is a component that's called optimizer, and it basically explores the space of all possible execution plans that can be executed. So once you determine what's the best optimal plan to be executed, you start executing basically that at runtime. So what happens at runtime is basically that every single row goes to that operator tree and traverses basically the operator tree, and ultimately we deliver the results. The batch processing basically does pretty much the same thing, but does for a batch of rows. So think of it as rather than processing the data on a row-by-row basis, we take 1,000 rows, and then we push that segment or batch of data to the operator tree and deliver the results to the end user. Obviously, one is that you get better performance. We save some CPU cycles. And ultimately, there is performance benefits for all of this. I would say for now, this is kind of the new query processing paradigm for SQL Server that applies just to column store. However, you can apply the same concept for row store too, right? So in the future, you'll see us innovating in that area too. But for now, this is column store specific only. Okay. All right, so just reiterating the benefits. Clearly, we get the reduced I/O. We get the better compression because we are operating within the same domain, and runtime performance improvements. All right, let's talk about what's new, what's coming. All right, so when we introduced SQL Server 2012, basically we were happy about the fact that we introduced column store technology because that's not many RDBMSs in the world actually have this functionality. However, we did realize that there were some gaps that functional gaps that we didn't have. And some of the motivators for SQL 14, as well as for exposing this functionality for PDW, which is data warehousing appliance, was how could we actually patch these gaps so we make it actually more usable and kind of ready for prime time. So the gaps that were there is that, first of all, we introduced non-cluster column store index. And they were not updatable column store indexes, right? So you couldn't issue an update or DML operation. Another downside was that we have, I would say, relatively, I shouldn't say poor, but not as optimal memory management. So basically, if a column store was very aggressive how it consumes the memory, at least used to be. And basically, we would try to allocate as much memory at runtime as possible. But that we realized that that's not as optimal always, because if you have large data warehouses, large tables, you cannot store all the data inside the memory. So we needed something else. There was a limited set of data types that you could use. For example, decimal, you couldn't use the full precision that you would expect from SQL Server, like 38 digits. There were some other data types that were not supported. And so basically, it was not, I would say, full SQL Server-like functionality. There were some gaps, basically, that we had. We spoke a little bit about the batch processing. We had a limited set of operators that were actually working as a batch in the batch mode. So, for example, if you do the inner join between two different tables, that was implemented as a batch operation. However, if you switch to, let's say, outer join, you wouldn't get the batch processing, right? So that was one of the problems, too. So when we started looking into this functionality after talking to many of customers, basically many of customers provided the feedback, this is really not optimal and how we would like it to be. And so when we set the goals for SQL 14 as well as how we expose these functionalities, we want to offer additional performance benefits. We want to offer leading compression ratio so you can actually store more data with the less disk usage, if you will. As well as we wanted to offer the functional parity, if you will, between the row store and column store. So for people who want to do data warehousing, who want to consume column store, it's still not fair to say, oh, you cannot use all the row store functionality that's available. Those are the functional goals. So let's talk a little bit about, I think there is 5, 6 slides that talks about specifically how we address the gaps that I spoke about in the past. So the first thing that we've done, 2012 version had a non-cluster column store index, which was the secondary index, if you will. So it required you to have both row table, and then you build a secondary index as a non-clustered index on top of it. So first thing that we did is we're introducing a cluster column store index. So the idea is pretty much similar to a clustered index in a row store, but here we are saying it's a cluster column store index. So what does it mean? So what it means is that when you define table with a cluster column store index, every column in that table is going to be automatically stored as a columnar orientation. Okay? So there is no choice. You cannot, like in non-clustered indexes, you had the choice to say, I want to build secondary index based on these columns. Here you are saying my primary representation of the data is actually columnar format. Clearly, there is a benefit of this is that you avoid the data duplication, right? Rather than having both non-cluster column store index as well as the row store index, having the cluster column store index, you clearly save space that is being used on the disk side. Additional functionality that we introduced now, we actually expanded the data type support that can be used for cluster column store indexes. So now we have full decimal precision, we have unique identifier, we have nvarchar, varchar, so all these large data types too. So there is expanded support for the data types that are typically being used. One data type, actually two data types that are currently not possible to be used in the cluster column store index are nvarchar max and var binary max. Typically, those data types are not really suited for the column store anyways, so it doesn't feel like it's a big downside. All right, so one thing that I want to emphasize here is previously, basically, with previous functionality, we used to tell people, create your non-clustered indexes for the fact tables, if you will. So if you think about the traditional data warehouses schema, it's a star schema. So we used to tell people, create your non-clustered indexes for fact tables, keep your dimensions as a row tables because non-clustered indexes were not updatable. Okay? So, and typically you have updates on the dimension tables. And so that was the kind of the design pattern that we advise people do. After we made cluster column store indexes, as well as made them available, we're going to talk about the updates. There is really no reason to now use row storage or row orientation anymore, right? You can actually move all your tables, data warehousing tables, towards the cluster column store indexes and just get the benefits of cluster column store functionality. All right, let's talk a little bit about the update. So we made our cluster column store index updatable. So any DML operation, insert, update, delete, it's all supported. So let's talk a little bit about how that works. All right, so what we see here is basically a table that has 6 columns, and all of those columns are stored as a cluster column, as a column store technology, if you will. So we'll go a little bit around the internals and how this actually works. What I'm going to talk over here is actually all internal. From user perspective, you don't see this being happening. However, there is some kind of magic that happens behind the scene and how we enable updates on the column store technology. So row stores are really optimized for the DML operations, right? They're really, really fast in getting the DML operation. So what we've said is that why don't we actually merge the two? Why don't we use basically column store for the scan and all that good functionality that it brings, and then use a row store to enable DML-like operations. So what we've done is basically there is a column store format, and then there is a small, you can think of it, a 1 million segment or row group that exists together with the column store format that is in row orientation, right? So when you do an insert, a simple insert, it actually gets inserted inside the row store. Again, it's transparent from the end user perspective, but the data gets inserted inside the row store. So you may ask, okay, so what happens next? So it's coming. So once you fill, we spoke about the 1 million segments, 1 million row segments, right? So once you fill 1 million rows, there is a background process. Basically, first of all, what we do, we close that row group. We say you cannot insert any more data into this row group. And then there is a tuple mover, which is a background process that accesses this closed segment and moves it into columnar format. So there is a kind of the backend process that kicks in and converts the data, applies the compression, splits the columns into rows into columns, and then stores it as a columnar format. So you may ask, okay, so what happens if I fill one segment or one row group? What happens? Well, we open another one, right? So we open another row group. So there is no restriction that you can have only one single row group per cluster column store index. We automatically manage that, but it's possible to have multiple row-oriented row groups within one clustered index. Now, it's temporary because it's going to be automatically moved into a columnar format at some point, but there is possibility of having more than one row group as a row format. Yes?
What happens if at that time, because I might have on top of the data warehouse analysis services, okay? It would be very useful for roll-up partitions. Okay? What happens if I'm getting a roll-up query before the tuple has been moved?
Yeah, so the question is basically, as you accumulate the data in the row store, which is we call this delta store, as you accumulate that and you issue a query, what happens? What's the behavior? So what happens is basically that is at runtime, we unify the data. So depending on what you are looking from the query perspective, we unify the query that hits the column store as well as the row store. Now you may ask, is there no performance penalty for this? And I would say, yes, a little bit. However, if you think about 1 million rows, SQL Server is pretty damn fast querying 1 million rows. And typically you'll see that the column store format is actually much larger compared to what you have in the row store format here. We are talking about fact tables, which is billions of rows. So you're not even going to see any performance downsides, if you will, by having this small segment. Now, at some point, basically, it's going to get probably very quickly, as soon as you fill it, it's going to get transferred into column store. I would say from the user perspective, you're not going to even feel that there is a row store and performance issues by having the row store.
If during the query I would happen to find the situation for whatever reason, would it show up in the execution plan? Any kind of warning indicating that you are merging two sets?
No, it's all basically internal to the system. You have visibility. We have DMVs, and I'm going to demo that. We have DMVs that allow you to see how many rows actually are in a segment that it has been opened or closed and hasn't been compressed yet. But you should let the system basically automatically kind of compress it and move that into the column store. If you don't want to wait for a tuple mover to kick in, we have a functionality that allows you to actually manually move that data into the columnar format as needed. So we're going to demo this, but good question. All right, so how do the DML operations work on top of this column store and row store? So we said insert, simple insert values, just automatically gets appended into the row store. At runtime, when you query, we just unify the data, and then we deliver the results to the user. For update, well, let's go first talk about delete. Delete is implemented as a logical delete, meaning that we just mark this row as invalid, and we are not going to basically query this, and rather we would ignore this column at runtime when you query it. So you may ask me, so what happens if I have lots of deletes, right? I will never be able to reclaim my space. In fact, Columnstore is supposed to give you compression, but this keeps growing. So we allow you to actually, we have a rebuild functionality that allows you to reclaim unoccupied or occupied space that has been used by delete operations. So you can actually shrink back to whatever original or space needed is just for the actual data that hasn't been deleted. So there is functionality. Rebuild works for a whole index, if you will, or it can be per partition too. Okay, so update. Update is implemented as a composite operation, which is delete followed then insert. Okay. There is also bulk insert. So you may ask, well, what happens around the bulk insert? So if you're using, let's say, BCP, and you try to load data into a column store, what happens? So there is, I would say, there is kind of two modes that we have internally. So first mode is if you insert very little data, and there is a threshold, it's about 100K, 104K of rows, we will insert that data set into the row store. If you try loading data more than the threshold, we automatically employ compression algorithms, and we convert this data set into a column store, and we store it as a column store. So you may ask, why threshold? So the idea there is that ultimately there is a trade-off between how big your segments are, what kind of compression you're getting within the segment, at runtime performance, how many segments you need to scan to deliver the results at query time, right? And we found it that basically ideal segment size is 1 million rows. But with 1,000 row segments, we are still okay. We are performing quite nicely, but we don't want to create too many segments, if you will, too small segments, because then at query time you pay some penalty. We spoke about the tuple mover and manually invoking the tuple mover. So the way that that's exposed is basically through reorganized functionality. So you can issue alter index, reorganize, and any closed segment will be moved into a column store. If the segment is open, we are not going to reorganize. Doesn't do anything. Okay, segment has to be closed, or row group has to be closed. Yes.
In data warehouses, you said you want to be able to efficiently handle very large volumes of data. The sizes of the column stores, could I define those? Is there any knob, or those are?
So when you say sizes of, I'm assuming that you're talking about the sizes of the actual row group.
Correct.
Okay, so the question is row group, size of a row group customizable? So answer is no. So there is no knob that allows you to actually say how many rows you want inside the row group. However, there is runtime behavior. We automatically scale down or up depending on the memory that we have available. We're going to talk a little bit about that. So there is kind of runtime behavior, dynamic behavior of a column store as you load the data into the column store. All right. In fact, that's the very next slide. All right. So data warehousing, typical fact tables are very, very large tables, right? And we spoke about the DML, deletes are not being automatically deleted. There is a need to issue a build operation or rebuild operation. There is a need to issue a reorganize operation or build operation. So if I have a row store table, and if I need to move that now into a column store because I want to leverage the column store, obviously if you have billions of rows, you cannot just fit everything into the memory and convert it into a column store. So for these reasons, and I call these operations like build, rebuild, reorganize, utility operations, right? Because really it helps you kind of manage your data warehouse. So the way we implemented this is we have what's called like a streamable utilities, right? So the idea is that rather than processing all the data at the same time, you actually take chunks of data, you perform conversion to a column store, you store that data into a disk, and then you take new chunk. It's a streamable operator. You can think of it as a streamable operator. Right? So if I have billions of rows, I'm going to take 1 million rows. If I try loading billions of rows inside the column store, I take 1 million, I make compression, I store it into a column store, I take another chunk and keep doing that in a streaming fashion, rather than using up the whole memory, if you will. All right, so then what happens at runtime? So once you store the data into the column store, what happens at runtime? So we do pretty much the same process, right? Since you can have billions of rows inside the column store technology, and depending on what the query is asking for, you can actually project quite a few rows. We follow the same process where we basically perform execute the query, and then we stream and load only kind of 1 million rows, if you will, at a time, and keep processing the data as needed. For people who are familiar with the 2012 and 2012 version of Column Store, the batch operator actually was not spillable, right? So it either fits the whole thing into a memory, or it basically goes back to row mode operation, and then it spills, right? Clearly, there is inefficiency in that, right? So we've actually implemented the hash-based spilling. So now we have batch mode spilling operator, and so the whole query executes in batch mode. Whether it fits into the memory or basically it requires spilling, it's going to execute into the batch mode. So let's talk a little bit about the segment sizes and how does it actually work. By default, we create 1 million segment sizes. Okay, so we always want to create 1 million segments because we find that that's an optimal size for a row group. However, depending on your table design, so your table can be narrow or it can be very, very wide, right? Your memory requirements in order to store 1 million rows in the memory actually varies, right? If I have 3 columns versus 50 columns, obviously the memory requirements are different. So the way we've designed this is actually the behavior is that by default, we try to load all the data into memory and build those 1 million segments. However, if we cannot fit all the rows into memory, we actually try to first reduce the DOP, so degree of parallelism. And even if that is not enough memory, then we start scaling down the segment sizes. Okay, so we dynamically start scaling down segment sizes. We also allow you expose a couple of DMVs that you can go and see, what's the quality of your segments, if you will. So if you see something that is not 1 million segments, that means basically that most likely you didn't have enough memory to store all the data, 1 million rows inside the memory, and we scaled it down. So typically, that should trigger an action at some point, let's say once a week. You go and evaluate what are the segment sizes. You dedicate a little bit more memory to certain processes, rebuild processes, and you rebuild your partitions as needed. So you get those 1 million segments, if you will. There is another reason why you would not be seeing 1 million segments in the column store, and that has to do with the dictionaries, right? So the way compression is implemented is basically we build dictionaries, and sometimes dictionaries cannot fit inside the memory, and then we basically split it, we close that row group, and then build another dictionary. So if you have very, very wide varchar columns that need to be compressed, it's possible that you fill up the dictionary space, and then the segment kind of gets broken into a less than 1 million row size. All right, so let's speak a little bit about the performance and how this works. So I mentioned basically that previously, we had very few batch operators. So specifically, we had inner joins for implemented as batch operators. However, if you try to do, let's say, outer join or local global aggregation, that wasn't implemented as batch. And clearly, there was some performance benefit or downsides of not executing this as a batch operations. So in SQL 14, we fixed that. So basically, we have more batch operators, and now we can execute more and more parts of a query execution plan as a batch. Another thing that we did is that, again, I'll contrast with SQL 2012, is that if you had a plan that had a combination between the batch operators as well as the row operators, by default, we would switch completely into row-based execution. Okay? So in SQL 14, we actually allow mixed mode operations. So whatever can be executed in batch mode, we execute that batch mode. You basically get performance benefits from that. And then whatever, where we don't have batch operator implemented as yet, we execute that in the row mode. So you get the benefit of, performance benefit of the existing batch operations, if you will, at runtime. We spoke a little bit about what happens if I need more memory at runtime to when I perform, let's say, hash join. So we implemented the hash-based hash join streaming, so we can actually completely execute the whole hash join in the batch operations. Again, huge performance benefit compared to what we used to have. All right, so let's talk a little bit about performance numbers. So what I'm going to show you a couple of graphs, and the graphs are based on the parallel data warehouse. So this is not SMP and SQL Server, but still I think it's a good indication kind of the performance benefits that we see from using the row store versus the column store. And what you see, this is actually customer workload. I didn't name customer here, so this is actual customer workload. And you see that the actual mileage and performance that you get actually varies, right? There is no a silver bullet that says every single query is going to be improved by 5x, right, or 10x. But I think on an average, if you have a workload, you could expect between 5x and 10x performance improvements by moving to Columnstore technology. All right, so two more metrics. These are the data points for TPCDS and TPCH. We use 3 terabytes, I think 5 terabytes of the data sizes. And again, you see that there is huge performance benefits, 5x performance benefits, 20, 30x performance benefits in some cases. But again, there is no silver bullet that says every single query is going to improve. So your mileage can vary. But again, between 5 to 10x, that's something that you should expect from the Columnstore technology. All right, let's talk a little bit about the compression. So we mentioned that we can actually implement better compression compared to a page compression because now we are operating within the same data domain. So there is two flavors of compression. And yeah, so when you create a cluster column store index, so if you have, let's say, heap or a cluster index table, row store table, when you create a cluster column store index, by default, you get a default column store compression. And you can expect probably 5 to 7x compression compared to the raw data or in the data in the files. And I would say if you compare that to page compression, you get probably about 2x additional compression compared to page compression, right? So think about it. I have 10 terabytes of data in the file. I load that into a column store and I get 1 terabyte, right? We spoke about terabyte, price per terabyte, so huge benefit by going to column store technology. There is also another option where you can actually get additional compression, and typically data warehouses basically keep your data sets for quite a few years, right? So there is a notion of hot and cold data, right? So we introduced also what we call archival compression, where for those data sets that you're not querying as often, basically you can employ additional compression ratio. So you probably get about 30% additional compression by using the archival compression. And you can actually, this archival compression works either for a table or column or the cluster index as a whole, or you can do per partition. So you can have, let's say, 15 partitions, and you can actually specifically use the archival compression for one partition if you wanted to. You can also go back and forth between column store compression and the archival compression if needed. So if you find that you have enough storage to actually store the data, you can actually go back to your default columnar compression if you wanted to. Yeah?
Question. Now that you're talking a little bit about numbers, what impact have you seen in CPU consumption? Because of course, you have to decompress and transmit.
That's right. That's right. So the trade-off, so the question is, yes, I get good compression. Is there a trade-off with CPU? The question, they are absolutely right? So if that's the reason why I said basically there is hot and cold data. So we would want you to use archival compression for not as oftenly queried data because there's more CPU cycles required to decompress the data sets. But if you're not querying that data set as often, I would say it's okay to use the archival compression because there is additional storage that you gain.
Compared with the traditional row store?
So I would say, again, so you get, compared to page compression, you get, with column store compression, you get 2x, approximately 2x, and this gets additional 30% compared to a column store compression.
Okay, and CPU costs?
That's a good question. I don't have the numbers, but that's a good question. Yeah.
You need to understand that.
That's right. That's good. A good question. Which compression you use, it's exposed as in sys partitions, so you can always kind of assess what are the partitions and what are the compression modes that you're using. All right, time for demo. So what I'm going to do, I'm going to demo PDW, but again, the functionality that you see is pretty much the same as SQL 14. All right, so let me just log in and switch screens. All right, so what I have here is I have a couple of databases. I have AdventureWorks DW 2008, which is all the tables in there are either heaps or clustered indexes. So let me go and use this database. Okay, so the first thing, let's go query and see what are all the objects that we have in there. Yeah, I can't do that. Yeah, can everyone see, or it's hard to see? Hard to see? Yeah. Actually, where do you? Control N? Oh, there we go. Okay, awesome. Is this better? All right. I learned something. Thank you. All right, so you see that all the tables are either heap or clustered indexes. So what I'm going to do first is PDW exposes CTAS functionality, which is similar to select into in SQL Server. So what I'm going to do, I'm going to create a new table based on the DIM account, and I'm going to create a clustered index table. and I'm going to create a distributed table in PTW. So PTW has a notion of two table sets. One is replicated, the other one is distributed. Distributed means that we're going to spray out the data across different nodes that you have in the system. So we are using the distributed table here. So the next thing I'm going to do, I'm going to create a clustered index on top of this. Okay, so we spoke about converting row store table into a column store. So what I'm going to do here is I'm going to create a cluster column store index based on the clustered index that already exists on my table. So I'm going to execute this. Okay, so table got created. So if I go now and execute my show me all the objects in the database, you see that Igor table is with cluster column store index. Okay. So you can also go back and forth between cluster column store as well as the row store. So you can go back and forth between the row, from row to column store and from column store to row store. I don't expect that this is a typical operation, but I want to show it basically so you guys know that you can kind of go back and forth between column store. Once you convert to column store, you typically for your data warehousing use cases, you'll find that this works just fine for you. Okay, so I'm going to drop the index, and if I go and requery my objects, you'll see that, oops, wrong button. Now my Igor table became the cluster table, okay? So I'm going to even drop the cluster index. So I'm going to convert this table into a heap, and I can also go from heap back to a column store. Okay? All right, so let's do something more fun. So the next thing is basically I'm going to create a temporary object based on the cluster column store object. So I'm going to create a temporary table with the cluster column store orientation, and we're going to do some DML operations. So let's see how the system behaves. All right, again, I'm using CTAS operation. I create a temporary object. It's called temp_cci. Let's go and query this. So I get 100 rows or something, and I'm going to do the insert, a new row into this. Anyone can tell me what happened behind the scene? Where is the data? In the Delta store, right? So I do the select. Here is my record that I inserted. Again, from the user perspective, this is completely transparent. Okay, let's try an update. Okay, if I now go and see what happened, I see that my value is now updated value. Okay. And then let's delete the record. And if I search for it, it's gone. Okay. So the next thing I'm going to show is a little bit of the DDL operations, right? So when I create a table with a cluster column store index, by default, all columns are now column store orientation, right? So clearly, if you contrast that with the clustered index for the row store, when you create a cluster index, you specify the keys, and typically, once you define your keys for a cluster index, you cannot change them, right? They are static. You cannot change them. Initially, we were thinking basically, so now that you define the cluster column store index, and all the columns are part of your columnar orientation, we do need to actually enable kind of DDL functionality because people evolve their schemas, right? So we actually do allow adding new columns, dropping columns, modifying columns. So pretty much any DDL operation that you are used to with a traditional row store is available. Okay, so let's see what happens. So I'm going to add a new column into the table that we previously created, and I'm going to project the data from it, and I see my new column being added. Okay. If I drop that column, again project, it's gone. Okay. All right, so let's talk a little bit about what happens behind the scene. We spoke about the Delta store. You asked, there was a question, can I see how many rows I have in a Delta store? Can you help me kind of manage all of this? All right, so we have a couple of DMVs, but I think the most important ones are column store segment as well as the column store row groups. Okay, so if I'm going to query this column store row group, So what you see here, since this is a demo of PDW, so first thing you'll see that there is 2 nodes. So I have 2 SQL Server instances. Well, not really, because I'm doing the demo of a virtual appliance. But there is 2 nodes. And then in PDW, we spoke about the distributed table. There is a notion of a distribution. So within each node, we actually split the data across 8 distributions. So that's why you see kind of 8 instances, data instances for each node, if you will. And all of the data is in compressed format, right? Because I used my row store, converted that into a column store, ultimately built the column store for the first time. All right, so let's do a simple insert into my table. And let's see what happens now with the data. So there is one open segment, right? And it's a delta store. You see there is one row, third row from the bottom. It says it's an open segment. So we didn't have that before, right? If I keep inserting the data, basically this is going to grow. You'll see 1, 2, 3, and you'll see actual number of rows inside the delta store. We spoke about the ability to actually use reorganize and move the data from row store into a column store. So let me execute that. So question, when I query now row group, what I'm going to see? Am I going to see all the columns being in compressed format? Some people shake yes, no. So I'll tell you. If you recall, basically what I was saying is that only closed segments can be moved to a column store format if you issue reorganize, right? In order to move data from open segment into a column format, you need to rebuild, okay? So let's do that. So I have a second statement here that says rebuild, and you can issue rebuild for all partitions or for single partitions. It's up to you. So let's do rebuild. So at this point, we're going to rebuild the whole index. Rebuild operation doesn't just take the row store table or delta store. It actually takes the data stored in the column store and delta store, unifies it, and recompresses it again. Yes?
Is there any number to indicate you want to force it to only do it for the delta store?
No, no. At this point, yeah.
All or nothing?
When I say all or nothing, it's once you reach the 1 million segments, once it gets closed, at that point you can move it manually into a column store. If you want to move it, basically everything, then you do the rebuild. All right, so I have just 1 or 2 additional statements. So how many people have heard of Polybase in PDW? All right, so we have a functionality basically where in PDW we enable a kind of T-SQL interface on top of the Hadoop data. So you can actually use T-SQL-like statements on top of Hadoop. But we also enable bidirectional interface between Hadoop and PDW, which is the relational source. So you can think of it basically, we unify both relational and non-relational data and expose that through T-SQL interface, if you will. So I have some data in Hadoop, a couple of 60,000 records or so. So what I'm going to do, I'm going to use the CTAS operation to move my data from Hadoop to a cluster column store. Actually, let me show you the table so you trust me that I'm not cheating here. So I have, all right, so it's AdventureWorks CCI database and Internet Sales HD. So that's the table. Let's see the view the code. All right, so what you see is basically traditional table structure, and then there is location, which actually points to a HDFS that's in the Hadoop. Okay? So I'm going to execute this, and it's done. Okay, so we can now go and query this table. And I have 60,000 records that I had there, right? So this is basically going from Hadoop to CCI. I have also example of moving the data from relational, in this specific case, going from CCI back to Hadoop, right? And the use case here is that you have a data set that you basically don't query as often, so you want to archive this into Hadoop. And then at any point in time that you want to actually go and query this data set again, you can actually move it back to relational store if you wanted to. All right, so I think I need to just create different objects here because I used that before. So I'm going to create Igor CCI 3 folder on the Hadoop side. I'm going to select data from my Igor CCI that I created, and that's it. So I'm going to create external table, which is the indication that move the data to Hadoop at this point. Okay, that's done. And so let's do a query where we query this data that's stored in Hadoop. Again, 60,000 rows that we had before. If I do refresh here, I should see another table. Actually, it's going to be within this database. Okay. Let me see how much time we have. We have 25 more minutes. Okay, so one thing that I also wanted to show, although it's not really the purpose of this presentation, I want to show you basically how this data now gets exposed through any BI tool. Since we treat all these CCI objects or cluster column store indexes kind of internally, whatever you do that's on the server side, the way we expose this data to the external world is just as an ordinary table. So I'm going to use Power Pivot to access the data, basically cluster column store indexes from PTW. All right, so let me invoke Excel. This is my URL for PTW instance that we just created. Okay, so I'm going to go to Power Pivot, say Manage. All right, so in this case, basically, we want to import the data from database. PTW is SQL Server, right? And the way you access it and the way you connect from the BI tools is as you connect to any SQL Server instance. So you say import from SQL Server. I'm going to provide my URL. Let me see. Okay, so we had AdventureWorks DW. Well, actually, let me go back. Actually, it was CCI that no, actually, it was here. All right, so let's see what do we have. What tables do we have? So we should see Igor. Remember that was the CCI object, Igor CCI. Right? So if you go finish, oops, I didn't select any of these. So let me select Igor CCI. Actually, I'm not going to. That's going to be 60,000 objects. Okay, let's do it. And let's import that. So at this point, basically, Power Pivot goes to PTW and starts extracting the data from PTW. So 60,000 rows got transferred. And now I can query it and work basically with PTW, with Power Pivot or any other third-party tool as I would work with any other relational data, if you will. Okay, so this is the demo that I had in mind. So there is a couple of more slides, and we're almost done. All right, so let's talk a little bit about the design and things that you should consider as you start implementing the Columnstore technology. All right, so the first question that comes is, we have non-cluster column store indexes, we have column store indexes, cluster column store indexes, which ones should we use? Previously, I said basically that I personally don't see a reason why I would use non-cluster indexes anymore. I think basically that all tables should go into cluster column store indexes specifically for data warehousing purposes, especially because we improved much of the functionality what we offer, as well as they are updatable, unlike the non-cluster column store indexes. However, if you want PKs and FKs implementation, they are not supported right now with the cluster column store indexes. Right? If you want key enforcements, so there is still a use case where you want to use the non-cluster column store indexes. If you use non-cluster column store indexes, they are not updatable, so there is a best practice how do you actually refresh the data, partitioning, partition switching, and whatnot. Again, so I think from the functionality perspective, you should be using cluster column store indexes because there is huge benefits of moving to cluster column store indexes. All right, so once I create the cluster column store index, can I create non-cluster indexes on top of it? So answer is today, no. In the future, basically, we'll be looking into this. And the primary use case there is that kind of lookup type of queries, if you do kind of point queries, you want to kind of get to the next level of performance benefits from that. For that, I would say at this moment we are probably in the milliseconds lookup time for lookup queries, or time for lookup queries, but we can improve that further, and we will invest in improving this in the future. Partitioning, right? I mentioned once you move to cluster column store index, or for non-cluster column store index for that matter, you can still implement the partitioning strategy as needed. We advise people that you don't create as many partitions as you would traditionally with the row store, because now you actually get the compression and the you get all the data being stored as a column, so there is no need for as extensive partitioning as you would with the row store. However, there is still benefits of using partitioning. So typically, if you have those data sets that you don't query as often, you can actually create partitions, store them there, perhaps implement the archival compression, and save some disk space, if you will. All right, so how do you design the schemas? There is really no difference. So from what we used to say with the SQL Server 2012 and non-cluster indexes, we are still advising people that when you define or design your star schemas, avoid using basically strings as keys, because it's just not efficient. And traditionally, basically, for data warehousing use cases and star schemas, you create surrogate keys, and then you which are either int or big int data types, and then you do join between the dimension effect table. So just follow that best practice, and there's going to be clear performance benefits from doing that. All right, so you have an existing data warehouse. It's a row store. How do you move to CCI? Okay, so first of all, when you convert from row store into column store, it's a blocking operation, right? Meaning that there is no queries, because you are actually changing the actual storage engine, right? You're changing the storage of the data. So it's a blocking operation. So take some time, basically, if you have the offload time, and perform the operation. Before you can do conversion, drop any indexes, because you cannot create cluster column store indexes on top of the table that contains indexes, so just drop them. If you do have a cluster index, and I would say tables with the cluster index, row store tables with a clustered index converted into a cluster column store index actually there is benefit from getting a better compression ratios. So since the data is ordered, you can actually gain some compression ratio. So it's actually good practice to have if you're going from row store to column store, to build a clustered index on a row store, and there's going to be some disk saving once you move into column store. If you cannot perform offline operation, it's a traditional trick. So create the view, point that to your row store table, and then build another table with a column store index, and then you switch basically the view implementation to point to a new column store, a table with the column store technology, and just drop the old one. All right, that's all for what I had in mind. So we can open now for Q&A. Any questions? Yes?
In the new row store tables or objects, you have lock escalation, either from row to table or page to table. How is the locking structure now here in the
column store? So the question is basically lock escalation, locking behavior. How does that change at all with a column store? So the answer is no. Actually, column store is actually, the way we've implemented it is actually at the storage level. So it's very, very deep inside the engine, the way that it's implemented. So any functionality on top of it just works as is. So there is really no functional difference there.
So we would still be seeing locks at the page level, even though the object itself.
Well, if you use page locking, yes. If you use row level locking, you're not going to see it, right? Yes.
What isolation level are they compatible with?
Yeah, so the question is basically what isolation level can you use with the column store technology? Everything but the snapshot. So snapshot isolation is not supported at this moment, but everything but the snapshot.
What about read-permitted snapshot?
Read committed is
Read
supported.
committed is, but snapshot is.
Snapshot is not.
Thanks.
Yeah. Yes.
Maybe not so technical question. Do you think that the Columnstore indexes and the tabular databases are competitive to each other?
So the question is, if I have a tabular database, and I'm assuming you're talking about the Power View and something like Power, or OLAP or reporting services and the Columnstore technology, are they competitors? So in my mind, no. So in fact, I think we are seeing more and more customers kind of adopting the mix of the two, and it all depends what are the latency requirements that you have from the client perspective. We are seeing actually lots of customers now embracing the fact that we have the Columnstore technology, that you get actually runtime performance benefits, that they embrace the Columnstore technology together with OLAP, so you can have tabular model actually in direct query mode, and you can actually start pushing those queries and get answers from the database itself rather than having the latency and cached reports. But it all depends on the use case. What is it that you're trying to do? There is clearly benefits if you load the data into a cache, into memory. There is runtime benefits. If you pre-aggregate the data, there is benefits to that. But I think there is the second use case is I'm not willing to actually have the latency. I want to query the data as is. Or you can have a combo between the two where you have some level of aggregation for summaries, and then if you need to drill deeper, you go into a roll-up type of mode, and then you issue queries against the database. Sure. Yes?
In OLTP applications, it doesn't make pretty much sense to use Columnstore indexes, right? When we are dealing with the number of records up to 1 million or...
That's right. So the question is, if I have a Columnstore technology, is it applicable for OLTP? So I would say no. We designed purposely Columnstore technology for the data warehousing use cases, and the main idea there is that OLTP have like millions of records, and we don't want to interrupt basically performance of the backend process that goes and converts the data from row store into column store. You can update Columnstore technology, but it's not designed for OLTP use cases. So for OLTP use cases, you want to use your row store orientation. Yes?
Have you done any kind of testing internally, any numbers you could share by putting analysis services, multidimensional, not tabular, on top of data warehouse with Columnstore compared to row store, any performance gain?
Yeah. So I think, so the question is basically, is there any difference between row store and column store with SSIS, I guess, or all type of solution? I think the answer is going to be pretty much similar, right? Column stores are designed basically for efficient query retrieval, and specifically if you have certain queries where you don't need all columns from a table, right? If you're doing select star operation and you want to project basically all the rows, all the columns from a column store technology, you're not going to gain benefits. In fact, there is some performance penalty because you need to stitch columns together. So if you want to populate your OLAP solution from a column store, absolutely we can do that. But I think we want to focus column store technology on those use cases where you need to query the data in place and provide the query performance at runtime basically for those use cases. So I would say it's a collocation of the two. It's basically merging the two together rather than competitive. And as far as the performance difference, I don't have the access to those numbers. What I shared you basically specifically from just the column store technology, you can see exact same performance benefits. Whether you use SSIS, whether you use OLAP, or whether you use any other tool, the benefits are coming from the database itself. Yes?
Let's assume that we have a legacy data warehouse, let's say 2 or 3 fact tables, shared dimensions, region groups and stuff like that. So sometimes a lot of joins has to be performed. How Columnstore deals with such things?
Okay, so the question is, I have a relatively small data warehouse, right? I have 2, 3 fact tables, and then I have a bunch of dimension tables, right? And the question is, if I'm doing lots of joins, how does column store behave there? I would say that's actually why we designed the column store and why we had column store in mind. That's the reason why we actually implemented the batch of processing for join inner as well as the outer join type of join queries. And I would say column store actually shines for those use cases compared to row store. Any other questions? All right, that concludes our session. So please evaluate the session, and I'm going to stay a couple more minutes in case any of you have any questions.